All right, thank you, Dr. B. Good morning, everyone. Thank you for joining us today. My name is Manfredo Amurgo. I am the project manager for the Rogue One mission, and today I would like to introduce you to the preliminary design of the Rogue One mission developed by SPC. Today we'll be going through the mission summary, some concept of operations, the system of systems validation, the Vesta system validation, the Vesta subsystem validation, and finally some conclusions in programmatics. Today joining me are Assistant Project Manager Gino Ferra and Integrator Shane Evan Sanchez. A preview of our design team layout. As you can see, we have a project manager. We have two principal investigators for the respective vehicles with the respective design teams, and as well as an assistant project manager and a team of 2 integrators. The main purpose of this mission is, as stated, the reconnaissance operation for guided unmanned exploration 1. This is a mission that we're developing to obtain visual data from a remote area with unmanned vehicles. The following concept art depicts a visual representation up to date of the 2 main vehicles of this mission. The one on the left, the Vesta system, is a hexacopter that is being developed by Team Invictus, which is presenting with us today. And the one on the right is the ERAU system, which is the reconnaissance vehicle that is developed by Team Endeavor, and that will be joining us in the following presentation. Lastly, our third system, the ground station. This is the network interface that we'll be creating within these 3 systems that will be developed by both teams together. Now, I will guide you through the concept of operations of this mission. Starting by phase 1, the pre-flight stage. At this point, all the systems and main vehicles are taken from their respective locations and set up in both vehicles will be set up in the starting location, which is designated as the Mos Eisley Spaceport, and the ground station will be set up in this very building and the 3rd floor in the conference room. Moving on to phase 2, the transport to the Yavin 4 ruins. At this point, the Vesta system, their carrier vehicle, will be initiated from ground station to transport the carrier vehicle to the operations area, which is designated as the Yavin 4 ruins. This will be an autonomous flight that will be taken between these 2 major points and the path that we are calling the hyperlane. In these following graphics, we are able to see the preliminary path that we're expecting to have with the carrier vehicle and 3 major locations that have been studied and that will be approved in the following stages for landing in the operations area. The following animation in phase 3, the deployment of Aura, depicts how the vehicle, once it has safely landed, will roll out of the payload bay and start navigating the operations area. Phase 4 is a very reconnaissance of the Yavin 4 ruins or the operations area, where this reconnaissance vehicle will navigate across this operations area while live streaming video feed to the ground station, which is going to be in this building. After this vehicle has returned to the Vesta system, or the carrier vehicle, this will roll up the payload bay again and will dock again with Vesta for future transport. The docking mechanism is seen here with these servo motors that will help us to prevent any movement during flight. Phase 6 of this mission is the return to the Mos Eisley Spaceport. At this point, the Vesta system, or the carrier vehicle, will transport back the reconnaissance vehicle to the starting location through the same hyperlane or the same flight path, but in reverse direction. The following animation depicts the expected flight, which is not to scale, but is previewed to be expected to be like that. Finally, our phase 7 of this mission is our post-flight, which at this point all systems will be shut down and will be taken back to the respective locations. As well as the ground station systems, all the data will be saved and disassembled. The following design structure tree depicts the respective partitions of all the systems for this mission. As you can see, we have 3 major systems: the Vesta system, the Aura system, and the ground station. All these systems have their respective subsystems and components that have been developed as a preliminary design. Now, talking about the system of systems objectives, we have 8 primary objectives for this mission, which state that the Aura and the Vesta systems should be initiated at the Mos Eisley Spaceport, or the starting location. the Vesta system should transport the ERAU system to the Yavin 4 ruins or the operations area. The ERAU system should be deployed after the Vesta system has landed in an approved landing area within the operations area. The ERAU system should navigate within this operation area. The ERAU system should generate detailed images of the operations area, should transmit visual data to the ground station, and should return to the Vesta system after the visual data has been transmitted to the ground station. Finally, the Vesta system should transport back the ERAU system to the Mos Eisley spaceport after the ERAU system has returned to the Vesta system. The system of systems has currently 4 constraints which state that the system of systems will cost less than or equal to 3,800 United States dollars. It will have mission duration less than or equal to 60 minutes. The Vesta system will land in aggressive portion of the operations area, and the ERAU system will navigate through the aggressive portions of the operations area. Now, I would like to pass it on to my colleague, Benavides, Great, principal investigator of the Invictus team, which will be taking you into the Vesta system preliminary design.
Thank you, Manfred. I would like to begin by introducing the rest of the Invictus design team. With me today are Julia Mihailov, Lucas Iskowski, Jonathan Hamburger, Renee Spear, Brandon Dudley, Kyle Walker, and Jason Hamburger. The design team is structured as follows, and I'd like to point out that Julia Mihailov, Kyle Walker, and Renee Spear are sub-team leads, and we are divided into 3 sub-teams. The Vesta system is shown here on the design structure tree. It has 4 primary objectives: that it should transport the ERAU system from the Mos Eisley spaceport to the Yavin 4 ruins, that it should deploy the ERAU system after landing in an approved landing area, that it should then transport the ERAU system back to the Mos Eisley spaceport after the ERAU system has returned, and the final primary objective is that it should be operated under autonomous control. The Vesta system has 1 secondary objective, that it should be capable of relaying the photographic data from the ERAU system to the ground station system. The Vesta system has 6 constraints: that it will land in a grassy portion of the Yavin 4 ruins, that it will return to the Mos Eisley spaceport in less than or equal to 60 minutes of leaving it, that it will have a budget for its development and operation of less than or equal to 2,000 United States dollars, that it will have a flight time of less than or equal to 5 minutes, and that it will ascend to an altitude of greater than or equal to 3 meters and less than or equal to 120 meters. The Vesta system has 5 requirements: that it shall be capable of a ground speed of greater than or equal to 5.1 meters per second, an ascent speed of greater than or equal to 0.4 meters per second, and a descent speed of greater than or equal to 0.36 meters per second. The Vesta system shall also have a mass that is less than or equal to 9.5 kilograms, and planar dimensions that are contained within a 3-meter diameter circle. At this point, I would like to draw your attention to the model that we have here, and I'd like to point out a few key features of the Vesta system. As you can see, we have 6 motor propeller pairs. They will each be powered electrically through 6 LiPo batteries. There will be a 7th LiPo battery pictured here in gray that will be powering all of the other electronic components. We have those situated in the center of the design. That would be the onboard computer, the IMU, the GPS, and all of our attitude determination. We also have ultrasonic rangefinders positioned around the payload interface that will be used to determine our position relative to obstructions in the mission environment. And I would like to draw your attention to how the ERAU system will ascend the ramps into the payload interface, which will be made of polycarbonate ABS plastic and printed at the Rapid Prototyping Lab here on the Embry-Riddle campus. The aerial structure, which is a hexagonal design, will also be fabricated here at the AXFAB building out of isotropic carbon fiber. And I'd like to now go into the validation of the requirements for the Vesta system. Requirements 1.1 through 1.3 were experimentally validated through the use of a propeller motor thrust test. We mounted the propeller and motor pair on a thrust stand, and in the first test, which you can see on the left here, we ramped from 0% throttle to 100% throttle in increments of 5%, and then stayed at each percentage for 15 seconds. As you can see, the max thrust that we measured was 52 newtons. In this right graph, we did a second test where we rapidly ramped from 0% throttle to 100% throttle, and then performed the same increments in a descending pattern. As you can see, that produced a max thrust of 61 newtons, and using both of these, we were able to determine that relative to the weight of our system, which is approximately 122 newtons, we will be able to produce positive thrust and accelerate, therefore meeting our velocity requirements. The requirement 1.4 for the Vesta system was not numerically validated, but the way that we went about trying to validate it was using CATIA to design certain aspects of the model, such as the aerial structure and the payload interface. In CATIA, you can apply a material to your volume, and then it uses the density of that material and the volume to give you an estimated mass. This payload interface was approximately 0.166 kilograms. We did that for all of our CATIA design models, applying the proper material, and then we pulled other masses from the spec sheets of the products that we will be purchasing. I'd like to call your attention to the aspects that generate the most amount of mass, mainly the ESCs, which are the electronic speed controllers for each motor, the 7 batteries, the aerial structure, the payload interface, and the motors. All in all, this comes to approximately 10.0591 kilograms, which does not meet the 9.5 kilogram requirement. We expect to be able to improve our design and meet this requirement next semester during critical design. The requirement 1.5 for the Vesta system was numerically validated through the use of CATIA again. We measured the distance from one extent of the aerial structure to the other and found that it was approximately 1.16 meters, which validates that we must be contained within a 3-meter diameter circle. So in summary, we validated all of our requirements either numerically or experimentally, except for requirement 1.4, which was not validated numerically and is pending to be experimentally validated next semester. I'd now like to go into the risks of the Vesta system. On the row axis will be probability, with 1 on the bottom and 5 on the top, 5 being the highest chance of the risk occurring. And then severity on the column axis, which goes from A, negligible, to E, catastrophic, catastrophic on the right, and negligible on your left. These definitions will be used throughout the presentation in the subsystem risk matrices as well. So the first risk is that there may be high grass in the Yavin 4 ruins area. That is very high probability, but low severity. The second risk is that there may be poor weather conditions on the day of the test. That is about medium probability, 40 to 60%, because weather is difficult to predict. And it is high severity because in poor weather conditions, we would not be able to conduct the mission. 3 is that there may be collision with objects in the hyperlane, which is the area between the Mos Eisley spaceport and the Yavin 4 ruins. That is low probability, but high severity, because if we were to collide with something, that would cause damage to our system and to embry-riddle property. To mitigate these risks, for one, we would examine the height of the grass in the Yavin 4 ruins prior to mission commencement, and we would cut it ourselves if necessary. 2, we would choose a test date that had favorable weather conditions for the operation of the Vesta system. And 3, we would not fly the mission if our attitude determination requirements were not met. I would now like to welcome up Julia Mihailov, who will be introducing you to the structure subsystem.
Thank you, Benedict. The structure subsystem definition can be seen on the slide with respect to the design structure tree of the Rogue One mission and within the Vesta system. The structure subsystem consists of the aerial structure component, the landing system component, and the payload interface component. The structure's subsystem objectives include that the subsystem should sustain the structural forces incurred during the mission. It should provide a frame for mounting the other subsystem components. It should secure the ERAU system to the structural frame of the Vesta system during the mission flight. It should deploy the ERAU system upon landing. The component requirements satisfying the structure's subsystem objectives are included in the aerial structure component, the landing system component, and the payload interface component requirements. These requirements are that the aerial structure component shall sustain a force greater than or equal to 234 newtons and less than or equal to 300 newtons as generated by the propeller's component. The landing system component shall be capable of withstanding greater than or equal to 9,630 newtons and less than or equal to 12,740 newtons. The payload interface component shall sustain a force greater than or equal to 20 newtons and less than or equal to 120 newtons applied in the nadir direction. It shall also be capable of releasing and securing the ERAU system to the Vesta system with a step height of 5 centimeters. The structure subsystem design, as shown on the slide, was created to satisfy the objectives of the structure subsystem. Of note are the aerial structure, the landing legs, and the docking ramp. The aerial structure component requirement 1.1 and 1.2 are restated on the slide above and were numerically validated through ANSYS APDL modeling and comparing the maximum stress found with the ultimate tensile strength of the isotropic carbon fiber material that will be used for the aerial structure. For requirement 1.1, we found a maximum stress of 0.0321 gigapascals, which is less than the 4.5 gigapascals ultimate tensile strength of the carbon fiber material, numerically validating this requirement. Similarly, requirement 1.2, we found a maximum stress of 0.0412 gigapascals, which is also less than the ultimate tensile strength of the carbon fiber material, in this case also validating this requirement. The aerostructure component requirement 1.1 and 1.2 ANSYS models consisted of a mesh of various sizing as shown on the slide above. The aerostructure component requirement 1.1 had a 234 Newton nodal solution model in ANSYS with a maximum stress of 0.0321 gigapascal maximum stress that occurred at the joining points of the aerostructure and the landing legs as shown. Similarly, the 300 Newton nodal solution for requirement 1.2 had a maximum stress of 0.0412 gigapascals, and this maximum stress occurred in the same location as the previous nodal solution. At this time, I would like to welcome up Lucas Iskowski to discuss the landing system component and the payload interface component requirement validations.
All right, thank you, Julia. So the landing system component requirements are restated as above. Requirement 1.1, for requirement 1.1, we found a maximum stress of 0.0242 gigapascals. This is less than or equal to 4.5 gigapascals, which is numerically validated. For requirement 1.2, the maximum stress of 0.0321 was found, and this is less than or equal to 4.5 gigapascals, numerically validating this requirement. Here you can see an example of the mesh that was used in ANSYS APDL. We have the coarse mesh here and the finer mesh around the circles being the mounting holes to get a better solution. Here we have the requirement 1, the landing system component requirement solutions for requirement 1.1. The maximum stress is shown up here. And requirement 1.2, the maximum stress is once again shown up there. In the callouts, you can see the placement of this maximum stress being in the mounting holes. Moving on to the payload interface component, the requirements are restated as above. Requirement 1, for requirement 1.1, we found a maximum stress of 0.0238 megapascals. This is less than or equal to 40 megapascals, which is the ultimate tensile strength of the ABS-PC plastic, which the payload interface will be made of. And for requirement 1.2, we found a maximum stress of 0.143, which is less than or equal to 40 megapascals. This numerically validates the requirement. This is an example of the mesh that was used to solve the solution in ANSYS APDL. Once again, you can see the fine coarse meshes. Moving on to the solutions for the payload interface components. We can see the maximum stress once again in this upper left-hand corner. The maximum stress was found in 2 locations. In this callout, seen in the left-hand corner of the payload interface. And the payload, the solution for requirement 1.2 is seen up here, and the requirement, the maximum stress is shown here, being larger, and in 1 location. Requirement 1.3 and 1.4 for the payload interface are restated above. The step height requirement has been validated because, as you can see, it is 5.786 centimeters. This is greater than or equal to our 5 centimeter requirement. Also, the payload 1.4 has been validated also, securing the ERAU system to the carrier. We are going to be using servos, which you can just see up here and up here to secure it in transit. These pink little squares are foam that will be used to cushion for it as we transit. In summary, we validate both the requirements for the aerial structure. We validate both the requirements for, numerically validate both the requirements for the landing system component. We numerically validate all of the payload interface component requirements. Here are a few risks that were identified to the structure subsystem. Risk 1, the subsystem requiring more space than can be supported. This is seen as a negligible risk because the subsystems have been communicating and we don't plan on having any more components. Force 2, this is seen as a risk 2, this is seen as a potentially catastrophic risk. Forces applied by unpredictable weather patterns. If the forces become greater than what we analyzed, this could cause the structure subsystem to fail. Risk 3, the Vesta system achieving an altitude larger than 3 meters and entering a free fall. If this happens, once again, this would go over what we analyzed the structure's aerial system for. This could cause failure to the structure subsystem. And finally, we have for 4 the collision with the ERAU system. This is seen as a medium risk because we plan to keep ERAU secure. To mitigate these risks, for number 1, we have maintained a proper communication between subsystems and have a space requirement planning for subsystem. For risk 2, we will apply, to mitigate risk 2, we have applying the factor of safety. This is also the same for risk 3. Finally, for risk 4, we maintain continuous communication with the ERAU system controller and install the appropriate sensors. I would now like to welcome up Jonathan Hamburger, who will be talking about the communication subsystem.
Thank you, Lucas. Shown on the screen is the communication subsystem with respect to the other partitions in the Vesta design structure tree. The purpose of the communication subsystem is to provide the ability to send commands to the Vesta system. We have 5 primary objectives for the communication subsystem, and that is that the communication subsystem should wirelessly receive operational controls from the ground station. It should wirelessly receive securing commands from the reconnaissance vehicle. It should wirelessly transmit operational data to the ground station. It should wirelessly transmit release commands to the reconnaissance vehicle. And lastly, it should interface with the onboard computer subsystem. The communication subsystem should also be capable of creating a relay between the ground station and the ERAU system. There's 3 constraints for the communication subsystem, and they are that it should transmit and receive on an ISM band centered at a frequency of 2,450 megahertz, and it also should be able to connect to the wirelessly local area network created by the ground station. We have 3 requirements for the communication subsystem. The communication subsystem should transmit with a bit error rate less than 0.01%. It should transmit with an isotropically radiated power greater than 27 decibel milliwatts. And lastly, it should receive with a sensitivity less than negative 76 decibel milliwatts. This is the solution that we have designed to satisfy the objectives, constraints, and requirements for the communication subsystem. It consists of an antenna component, a modem, and a power Ethernet hardware component. To numerically validate the first requirement, we use a carrier-to-noise ratio. Depending on the Wi-Fi protocol that we use for the mission, you will have a corresponding EB/NO ratio. With the Wi-Fi protocol that we have chosen, that corresponds to a carrier-to-noise ratio of 12.9 decibels. So as long as we have a carrier-to-noise ratio greater than 12.9 decibels, we will satisfy this requirement or validate this requirement. Currently, we are calculating a carrier-to-noise ratio of 34.2 decibels. Therefore, we numerically validate this requirement. Our second requirement is numerically validated by calculating the EIRP, the isotropically radiated power. This is found by taking the specifications of the antenna and the modem, so the antenna gain and the transmission power of the modem. As shown, we have an antenna gain of 4 decibels and a transmission power of 28 decibel milliwatts. This makes our EIRP 32 decibel milliwatts, which is greater than the 27 decibel milliwatts requirement. Therefore, this requirement is numerically validated. And lastly, the communication subsystem should receive with sensitivity less than negative 76 decibel milliwatts. This comes straight from the modem specification sheet. With the Wi-Fi protocol that we have chosen, we will be transmitting at a data rate of 24 megabits per second. And that makes our sensitivity negative 83 decibel milliwatts with a tolerance of plus or minus 2. Therefore, this requirement is numerically validated. In summary, all of our requirements were numerically validated. And now I'm going to be going over the risks of the communication subsystem. We have one high risk, and that's if we lose direct communication with the ground station. We also have 2 medium risks, consisting of a data rate greater than the network bandwidth or signal interference due to crowding on the network. These risks are mitigated by, the first risk is mitigated by transmitting directly through the ERAU system, and the other 2 risks, the medium risks, are mitigated by choosing a different Wi-Fi protocol. With the modem that we have selected, we are capable of doing this. And now I'd like to welcome up Renee Spear, who will be going over the propulsion and attitude control subsystem.
All right, thank you, Jonathan. Shown on the screen is the design structures tree, which shows the location of the propulsion and attitude control subsystem with reference to the other partitions of the Vesta system. There are 4 primary objectives for the subsystem. The first is that it should transport the combined Vesta system and ERAU system between the Mos Eisley spaceport and the Yavin ruins. It should provide stable flight for the combined Vesta system and ERAU system during flight. It should transmit attitude data to the onboard computer subsystem, and it should transport the combined Vesta system and ERAU system autonomously. In terms of constraints, it will operate at wind speeds less than or equal to 3.2 meters per second at 10 meters of altitude, and it will operate in optimal weather conditions. As far as requirements go, the subsystem has 8 requirements, the first being that it shall be able to provide a thrust-to-weight ratio greater than or equal to 1.5 to 1 and less than or equal to 4 to 1 with reference to the carrying load. It shall have a pitch angle less than or equal to 64.84 degrees, but greater than or equal to negative 64.84 degrees. It shall have a roll angle less than or equal to 64.84 degrees, but greater than or equal to negative 64.84 degrees. And it shall have a pointing accuracy greater than or equal to negative 2 degrees and less than or equal to 2 degrees. On the slide, you can see the solution that we have designed that will satisfy these objectives, constraints, and requirements. The solution consists of 6 18-inch by 5.5-inch ABS with carbon fiber inlay propellers, 6 E-Flight Power 60 brushless outrunner motors, 7 ultrasonic rangefinders, as well as 1 GPS unit and 1 IMU unit. We were able to experimentally validate requirements 1.1 and 1.2 using the thrust test that our principal investigator, Benedict Ray, earlier discussed. From the increasing thrust test, as shown on the left, you can see that the maximum thrust capable of being generated by a propeller is 52 newtons, and from the decreasing thrust test on the right, each propeller is capable of producing a maximum thrust of 61 newtons. Using this data, along with the combined system weight of approximately 122 newtons, we were able to determine that we are capable of providing a thrust-to-weight ratio of 2.55 to 1 from the increasing thrust test data, and a thrust-to-weight ratio of 3 to 1 from the decreasing thrust test data. Both of these fall within the range specified in our requirements, so they are validated. We are also able to numerically validate these requirements using a software called JavaProp. This software, it takes the geometry of a propeller as an input and provides several characteristics of the propeller as an output. The characteristic we're interested in is the thrust profile. Before completing analysis, one way to ensure that we are conducting the correct analysis of the propeller's geometry is to look at the sketch feature the JavaProp provides. The sketch of our propeller generated by JavaProp can be seen on the slide from the front view of the propeller as well as the side view. From this analysis, we were able to conclude that we are capable of producing a thrust-to-weight ratio of 2.16 to 1, which also falls within the requirements set for this subsystem. I would now like to welcome up Brandon Dudley to continue the discussion of the propulsion and attitude control subsystem.
Thank you, Renee. Requirements 1.3 through 1.8 are still pending numerical validation due to a problem that was discovered within the Simulink model used for the control law and the simulation of the flight. As can be seen above, a screenshot of our Simulink model, it was determined within the rotation matrices from the body frame into the inertial frame that there was an error with how that was being done. Now, we have determined this problem and are currently in the process of fixing it, but at this time, we are currently unable to numerically validate requirements 1.3 through 1.8, and as such, are still pending validation. In summary, requirements 1.1 and 1.2 have been both numerically and experimentally validated, as was discussed by Renee Spear, and requirements 1.3 through 1.8 are still pending numerical validation until the Simulink model can be fixed and able to numerically validate those for the control law. The propulsion and attitude control subsystem has identified 4 risks with the current design. The primary risk is risk 4, which pertains to the propeller motors not being synchronized with one another. Unsynchronized motors would generate a yaw within the Vesta system as it flies from the Mos Eisley spaceport to the Yavin 4 ruins, or from the Yavin 4 ruins back to the Mos Eisley spaceport. This undesirable yaw would cause the system to not go along the desired course in the hyperlink. In order to mitigate this risk, multiple tests will be done on the propeller motors well ahead of time before mission flight in order to calibrate and synchronize the motors to each other as best as can be done. Now, I would like to welcome up Kyle Walker, who will be talking about the onboard computer subsystem.
Thank you, Brandon. Pictured on screen is the onboard computer subsystem in relation to the other partitions of the design structure tree of the Vesta system. There are 5 primary objectives of the onboard computer subsystem. First, that it should perform all computations required by the carrier vehicle. Also, that it should interface with both the communication subsystem and all sensors on board of the carrier vehicle. And that it should save all input and output data to the onboard computer subsystem. Furthermore, 5 constraints have been placed on the onboard computer subsystem. First, that it will assist the electrical power subsystem in regulating the electrical power supply to hardware interface with the onboard computer subsystem. Also, that it will provide both a power over Ethernet and powered universal serial bus port, and that it shall provide I2C and SPI interface protocol capabilities. From these, 25 requirements have been generated. First, that it shall have a processing speed of greater than or equal to 8 megahertz and less than or equal to 2.4 gigahertz. That it shall provide greater than or equal to 1 pin that is grounded with respect to the power supply to the onboard computer subsystem by the power supply component of the electrical power subsystem. that it shall provide greater than or equal to 1 power supply pin with a supplied voltage of greater than or equal to 3.1 volts and less than or equal to 5.5 volts. Furthermore, that it shall provide greater than or equal to 6 serial input-output pins, that shall provide greater than or equal to 7 pulse width modulation pins, and that shall provide greater than or equal to 6 analog input pins. That should also be capable of storing greater than or equal to 0.5 gigabytes of information and less than or equal to 16 gigabytes of information. That it shall regulate the idle amperage supplied to the inertial measurement unit to less than or equal to 12.8 microamperes, and that should regulate the operational amperage supplied to the inertial measurement unit to greater than or equal to 3.10 milliamperes and less than or equal to 6.10 milliamperes. That it shall regulate the idle amperage supplied to the ultrasonic rangefinders to greater than or equal to 1.5 milliamperes and less than or equal to 2.5 milliamperes, and the operational amperage to greater than or equal to 10 milliamperes and less than or equal to 20 milliamperes. That it shall regulate the idle amperage supplied to the global positioning system module to greater than or equal to 4 milliamperes and less than or equal to 5.3 milliamperes, and that shall regulate the operational amperage to greater than or equal to 50 milliamperes and less than or equal to 100 milliamperes. Furthermore, that it should regulate the electrical power supplied to the modem to less than or equal to 107 watts and the voltage to less than or equal to 24 volts, and that should regulate the voltage supplied to the servo motors to greater than or equal to 4.8 volts and less than or equal to 6 volts. From this, the following solution has been engineered to satisfy these objectives, constraints, and requirements placed on the onboard computer subsystem. Of note is that we have selected the Raspberry Pi 3 Model B+, along with an Adafruit 16-channel PWM servo hat, along with 2 Adafruit 4-channel ADC breakout boards, and a 16 gigabyte micro SD card. Furthermore, we have designed the following wire diagram that we would be happy to go into further detail with, but that has been thoroughly reviewed by Dr. Brian Davis on this campus. The selection of the Raspberry Pi 3 Model B Plus validates requirements 1.1 and 1.2 as it has a processing speed of 1.4 gigahertz. Requirements 1.3 through 1.6 are also validated by the selection of the Raspberry Pi, which has 8 ground pins, 2 3v3 pins, 2 5-volt pins, and 24 general-purpose input-output pins. The selection of the Adafruit 16-channel PWM servo hat provides us with 16 PWM outputs, which is greater than or equal to the 7 required pulse width modulation pins. The selection of 2 4-channel ADC breakout boards validates requirement 1.8, which requires greater than or equal to 6 analog input pins. Requirements 1.9 and 1.10 are both validated by the selection of a 16 gigabyte micro SD card, which is capable of storing just over 15.9 gigabytes of information. Requirements 1.11 through 1.21 are summarized on the screen. In order to validate all of these, if the maximum operational amperage supplied to all the sensors on board is capable of being supplied, then all these requirements are validated. The Raspberry Pi is capable of, in theory, supplying 2.5 amperes to all peripheral units. That number is actually slightly lower than 2.5 amperes as it requires some power to power itself, but it is significantly greater than the 246.10 milliamperes required maximum amperage required to power all peripheral units. Requirements 1.22 and 1.23 are validated through the selection of a 3 amp DC buck converter or voltage stepper, which will step down the power to the modem component. And requirements 1.24 and 1.25 are also validated by the selection of the 16-channel PWM servo hat, which is capable of supplying 5 volts to the servo motors. In summary, all 25 requirements have been numerically validated, and we have identified 3 main risks to the onboard computer subsystem. First is damage from external factors, which we believe to be a low yet catastrophic risk. Second is damage from internal factors, which we believe to be a very low yet catastrophic risk. and various software risks, which we believe to be a low yet critical risk. We plan on mitigating any risks from damage from external factors by properly mounting any hardware on board of the Vesta system and by implementing safe landing fail-safes in our operational controls. We plan on mitigating damage from internal factors through having an expert review our wire diagram to ensure that we have interfaced all sensors appropriately. We plan on mitigating software risks through paper design and paper testing, time management, code review, and thorough testing of the code implemented. At this time, I would now like to welcome up Jason Hamburger, who will be discussing in further detail the electrical power subsystem.
Thank you, Kyle Walker. So shown here is the electrical power subsystem. Of note, there are two components, the power supply component and the power regulation component. Them being the purpose of them to supply power to the components for Vesta and the power regulation component to regulate that power as needed. So the two main objectives for the electrical power subsystem is that it should house the power supply component and house the power regulation component. The one constraint for electrical power subsystem is that it will be assisted by the onboard computer subsystem in regulating the electrical power supplied to the hardware interface with the onboard computer subsystem. Pictured here is our current design solution for these objectives and the constraint. Of note, we have the electronic speed controllers, and then we have 6 motor batteries, again, 1 for each motor, and a components battery, which would then power all the different components for Vesta. And then we have 3 step-down converters, otherwise known as buck converters. So as Kyle mentioned earlier, this is our wire diagram. So I'd like to mention that. So we have the objective to supply power as one of our objectives. So there are 6 modules here, as you can see, and so there are 6 motor batteries there. And then above we have our components batteries. So that fulfills our objectives for supplying power. Now for regulating power, I'd like to focus first on one of the motor components. So zooming in, we have the motor up top, and then we have the ESC, or the electronic speed controller. And so what this does is this allows us to throttle our voltage, and so doing that allows us to throttle the motors and generate more thrust. And so that helps us to regulate that electrical component. Additionally, on the side here, we have a voltage sensor. This lets us know how much voltage we have left in our battery. Moving back to the wire diagram and zooming in on the components, we additionally have 2 fuses to help us regulate any surge in power. So what this does is if we get any power surges, these fuses would break and we'd be able to replace cheap hardware components rather than frying the entire component array. And so that helps us to regulate power surges. Additionally, we have the step-down converters. And what these do is they take the raw voltage off the battery and they just convert it to what we need, for example, 5 volts or 24 volts. And then off to the side, we additionally have a voltage sensor to, again, show us the voltage in the battery. And then off to the side, it's been cut off. Oh, no, it's right there. The Raspberry Pi PWM hat, and that Kyle mentioned earlier. There are 3 main risks associated with the electrical power subsystem. One being connections failing to withstand mission forces, poorly soldered connections, and component damage when securing to the aerial frame. Overall, these are low risks. However, for mitigation, we decided through thorough testing, expert review, and again, thorough testing, and following specifications and recommendations, we can mitigate these risks, and they won't be critical factors for us. At this time, I'd like to welcome up Shane Evans Sanchez to conclude our presentation with programmatics.
Thank you, Jason. The total budget for the Rogue One mission is $3,800 US, with $220 going towards the ground station, $2,000 going towards the Vesta system, $720 to the Aura system, $180 to integration, and $130 to administrative. There will be $550 in reserve. The ground station has 4 main components. The modem will cost $90. 2 patch antennas will cost a total of $80, and the router component will cost $50. With the Vesta system, the A majority of the budget will go towards the electronic power systems due to the amount of batteries that are required to power the entire system. We currently have a Vesta reserve of $10. Here are the total labor hours for the management team. The total is 623 with a majority in the engineering. Here are the Invictus labor hours with a total of 2,506 with a majority again in engineering. We would like to thank the following individuals along with communities, more specifically Dr. Julio Benavides and Dr. Matthew Haslam for assisting with the concepts and development of this mission. We would also like to thank the panelists and the audience for joining us for our presentation today. Now I'd like to welcome back up all of the presenters and open up the floor for questions.
At this time, the panelists will ask questions to the team. We have about 15 minutes.
Okay, a comment first. Is this on?
Yes, sir.
Okay. A comment first of all, I thought that presentation was absolutely outstanding from all of you. That was great teamwork. I can already say that, remembering my account from last year, that was far, far better than anything I saw last year. That's not to say other teams today will be better, but you said it really outstanding. Fascinating project as well. Something I was missing right from the very start. How does it control the direction it's moving in? Do the propellers tip?
The propellers do not tip. We vary our pitch by changing the thrust that each individual propeller is.
So I can see that for pitch, I can see it for roll. Can you control yaw as well?
For yaw, I'd like to pass that to Brandon Dudley.
You want this?
Our current way for dealing with the yaw is changing the thrusts between the motors. As I mentioned earlier, if the motors are not in sync, we would accidentally generate a yaw. But by increasing the thrust in some of the motors, because half of them will be rotating counterclockwise and the other will be rotating clockwise. And with this, we can adjust the thrust in those in order to create the yaw.
Yeah, that's fine. That's what I was missing. And what happens, I mean, the grass being too long, you can do something about that. Lousy weather, you can do something about that. Hey, that's why I'm impressive. But what you can't control is wind gust. So what actually happens if you get a wind gust? Does it autonomously take you back on track?
The plan with the controller is to, yes, have the controller adjust for that wind gust. The current system determines what its thrust should be along that path, and if the sensors detect that it is accelerating faster than that, it will be adjusting to lower or increase, depending on where the gust is coming from, the thrusters in order to get along the desired location.
Okay. Final question and then also the final comment. What's the range that you're travelling over? I couldn't really tell from the picture. It might be 100 yards.
Isn't that back to Vesta?
So the range is approximately 78 meters. From the Mos Eisley Spaceport to the various landing sites, they only vary by a couple meters each.
Okay, so a question then is, relation to that is, I don't think you covered it, what's the risk of communications? Because at the end of the day, $1 billion spacecraft communications fail, so communications must be a bit of a problem. What's your fail-safe then, rather than it just carrying on forever and disappearing over there?
Right, so I would like to pass that to Jonathan Hamburger, who can answer that very well.
So we've done a communications test. So being on the 3rd floor of AC-1, we have direct line of sight of the mission area or mission environment. We've tested both at the Mos Eisley Spaceport and Yavin 4 Ruins, inside and outside. We've been able to communicate directly with all of it, and the way we're going to be setting up our code at the ground station is we'll send a start command, and then if we see something go wrong, we'll send an abort command that'll shut it down at any point during the mission.
So you can take over,
yes,
not autonomously, but manually, and then just lower it safely.
So the abort command should do that automatically, but we can look into a manual fail-safe if we need to override it as well.
Okay, fine. No, I thought it was great. And just a comment, because it was several times in the slides, several times you're going down to the second, in some cases third decimal places. there was a height measurement or something, I can't remember what, that was down in microns. And I'm sure you're not measuring to that, so it's just something to think of actually with your careers. You know, when you're writing down numbers, don't go down to silly decimal places because it really isn't, it doesn't add anything, and it detracts from what the main parts of the number is. But overall, I thought it was really very well done, guys.
Thank you.
Thank you very much.
I'd like to echo his thoughts and say that was a very good presentation, and I might have matched that with my notes. So I'll try to stick to the high level and I guess more pertinent questions. So the first thing, so you guys have probably seen that this system has been done before here on this campus, right?
Similar systems, yes.
Okay. So what are some of the historical technical challenges, and what are you guys doing to overcome them?
So similar things, we looked at a mission called Paul. They were dropping from, I believe, a height of about 5 meters, and their structure was using cold gas thrusters to decelerate. One of the things that we looked at was cold gas thrusters, but we determined that we had far more control using propellers, even though we're all astro, and we would have much preferred something that was more similar to what we were learning in our courses.
Okay. So part of the reason I ask that is part of my short career thus far is I've done a lot of concept development, and that is almost always the first question you get asked is what's been done before and what are you doing different? So good answer. Let's go down to we'll do a specific one. Slide 47. So you've got this indicator of a failure mode. What is the failure mode?
I'll pass that to Lucas Siskowski, our resident ANSYS expert.
Okay.
I believe it's mode 1. I'm not 100% sure about that. I can look that up and get back to you if you'd like to.
Okay. I was just curious, is it bending, is it going to tear? Because you said you're using
I believe it is tearing.
Okay. Okay. It was just curiosity. But let's see. So kind of another general question. So this is a reconnaissance vehicle, correct?
Our vehicle is the carrier vehicle that is transporting the reconnaissance vehicle to the mission location.
Okay. So maybe I didn't quite understand the big picture when you were starting this, but is the overall mission of this to be in a hostile environment like exploration? Is this meant to be a hostile environment in terms of combat? What?
So the idea is that this could be applied to various different environments and have different objectives. So one thing would be combat, another would be for search and rescue. Anywhere that you would want to deploy a rover that can go around and take video and images that you wouldn't want to send a person into.
Okay.
So it could be applied to various different locations, and combat is a very good one, yes.
Okay. So this isn't really a fair question at this point, but the question I'm leading to in this is how robust is your design to these situations? Can you withstand impact? Can you withstand damage? What happens when you take this damage? Part of the reason I was asking was when you're talking about electronics, you're talking about poor soldering joints. My thought was, okay, let's say prop strike on, say, orange. Can your electronics withstand them? Do you know? How do you test? Things, just simple things like that. But again, with the time you guys have, it's not entirely a fair question at this point.
So if I could answer that, a lot of what we did was build factor of safeties into our requirements that we were designing to. For example, one of those was in terms of building the landing legs, that subsystem component. We analyzed what a fall would be from 3 meters altitude, free fall with a approximately 13 kilogram weight. And we used that to generate the requirement for what the force that landing component should be able to meet. And so we do not expect to fall 3 meters, but we've built that into our system as a form of durability and redundancy. For electrical components, I believe there's a little bit of that as well, but to go into that, I'd have to pass it to Kyle Walker if you were interested.
Not at this point. When I come back next time, I'll ask.
Fantastic.
So, next one. So I thought it was awesome you guys experimentally validated your propellers for thrust. Did you guys perform initial calculations to determine how much thrust you could do? Or provide, sorry?
As in with respect to what the propellers and motor we would predict it to output? Yes. So that is what Renee Spear mentioned in her slides, where we did analysis with Java prop. And if you're more interested in that, I can hand it over to her and she can go into detail.
If you could, please, really quickly.
Absolutely.
So much time.
So we did not do any validation with the propeller and motor combination numerically. We only did that for the propeller itself to see what it was capable of generating.
Okay. Okay. So a follow-on question. I have this in my notes as well. This is just more something I learned through experience. The reason I'm asking that is that when you test your propeller, your motor may not be able to throw the wattage continuously. Maybe you guys already know that, so maybe I'm preaching to the choir, but it's something that we found out accident a few times, and I want to make sure you guys don't burn out in flight. Just so you guys know, I've got in my notes as well, the general rule of thumb is about 0.8 of the total wattage the motor can take. Okay, good, you guys, look like you know that. Because that's not something you want to find out when you guys it's real awkward. I guess one last general question. Have you guys already done your battery size?
I believe so, and I can pass that to Kyle Walker.
Okay. So the question I'm wondering here is, does your 7th battery need to be that big?
So the capacity on the 7th battery was generated from the absolute maximum amperage required by all components, and we had no way of confidently lowering that until we do actual testing next semester. We've already been talking to Dr. Brian Davis about how to test the wattage draw from our sensors during the test. At that point, we can then determine the actual capacity needed for the mission, and we can reduce that battery
Yeah, I was just
capacity.
curious because I was looking at like, I gave a 7.
Yes.
All right, I think that's all I have. The rest are relatively minor in comparison. Good job, you guys.
Thank you very much.
So first off, I'd like to congratulate you guys on being the 3rd Paul iteration. Good job.
Thank you.
So speaking of historical problems, I worked on Paul 2.0. So have you guys considered anything for like the wheel design or having powerful enough gear systems or motors in order to overcome having super tall grass? Because that was something that we definitely struggled with.
So I think that question would be better for the ERAU system who designed the rover. In terms of dealing with high grass for the propellers, we would expect to be able to cut the grass below where the propellers reach, and therefore we wouldn't have to spin them and be striking any tall grass.
Speaking of propellers, are those the actual propellers you're using, or did you?
Yes, so these are the actual propellers. We salvaged these from a previous project here on campus. We have we have quite a few of them. These are the worst. And then, these are the ones that were beat up. So as you can see, like there's chips on the end of the propellers, and they probably wouldn't produce the thrust you would expect. We have an additional 6 that are either new or in very good shape.
And you guys mentioned that your structure is made out of carbon fiber. Are you purchasing that, or did you go into any kind of like design criteria for why you're choosing carbon fiber?
Yes, so we did a lot of analysis with different designs of the aerial structure using different shapes as well as different materials. Some of those materials were aluminum, and what we would expect to do now that we've chosen carbon fiber, isotopic carbon fiber, is fabricated in-house at AXFAB.
So you guys are doing the layups yourself?
Correct, and it would be wet layup.
Oh, cool. So you're not using the pre-preg that I think Patrick had from like a million years ago?
No, we would be building a mold and using wet layup, and I can pass that to Lucas Siskowski to talk a little more about it.
Yeah.
One of the reasons that we don't use the pre-impregnated is because we get that, thankfully, from Boeing, but it is expired, so we don't want to use expired material. Beyond that, we also chose carbon fiber because we have an abundance here, so it is free, so that's why our structures budget is only $80 compared to Echo. Anyway, thank you.
Completely understand. That was why we chose carbon fiber too. So I think you guys mentioned you had an excess of budget in one of your departments. I don't remember what it was, but I highly suggest you use that to buy extra parts for your electronic subsystem, because you will end up burning a lot of those out, even just by accident, as we all learned last year.
So in our budget, we have built in that we are purchasing an extra motor as well as an extra ESC, and we could look into purchasing extra of other components as well. So that's a very good suggestion. Thank you.
Or should we get some of those static bracelets or something? Because I think we burned some out just because of the carbon and the SEL. Super exciting. Right,
Thank you all very much.
And we have time for one, maybe two questions from the floor. Anybody? Yes.
Hi, it was excellent work by all of you. There was already a discussion of portion of one of the requirements. And I just wondered, as part of the course, if you're teaching requirements traceability, that is, what is driving, you have a lot of specific requirements, and wasn't clear to me what was driving all of those requirements. So telling that part of the backstory is an important aspect of addressing your requirements along with your validation. And there was one in particular that I was puzzled by. I believe there was a structural requirement that was driven by the weather conditions. And I wasn't sure or not a requirement, there was a risk that you had listed as a fairly high risk that was driven by weather. And I'm not sure what you were expecting, how you were expecting the weather to affect you.
Right, so in our propulsion and attitude control subsystem, we have a constraint that refers to the weather conditions that we will be operating under. And so in the Vesta system, when I introduced that risk as poor weather conditions, what that was referring to are weather conditions that from that constraint we would not be able to operate under. And I can pass it to Renee Spear to explain what that constraint was if you would like.
Well, by weather, are you referring to wind, rain?
Yes, it was a combination of wind, rain percentage.
Yeah. So it might be helpful to specify what aspect of weather, what weather components you're most concerned about.
Understood. Thank you, sir.
Right, thank you.